Example 8.1. A single-slit diffraction experiment is set up with light of wavelength 420 nanometers, incident perpendicularly on a slit of width 5.1 microns. The viewing screen is 3.2 meters distant. A. Draw a picture of the situation and show N and alpha. On the screen, what is the distance between the first and second diffraction minimas from the center of the diffraction pattern? C. What are the widths of the central diffraction maxima and the secondary diffraction maxima? Let's put the given numbers into the single slit. So let's put the given numbers into the single slit setup. So from the question, A is equal to 510 microns. The wavelength is 420 nanometers, but usually it's not written in terms of nanometers, it's written in terms of microns. So if I move this over 3 decimal points, I get 0.420 microns. This right here is my preferred conversion for light. And then finally, the screen distance, they tell us, is 303.2 meters away. So if I think of a setup, I'm going to have a single slit. And then here's going to be my screen right here. So now if I start putting in my numbers, wavelength of 420, that's pretty close to the end of the spectrum. So I'm going to say that this is violet light coming in. And we know that its wavelength is 0.42 microns. Now the slit opening, or the aperture, is then going to be A equal to 5.10 microns. And then our final parameter is going to be D, which is then 3.20 meters. So if I'm going to show the sketch of the diffraction pattern, the first thing I have to do is I have to go calculate Nmax. So I'm going to start with the diffraction parameter. And that gives me, of course, Nmax, which then is A over lambda. And this will be 5.10 microns divided into 0.42 microns. And that's going to give me 12.1 for Nmax. So I now know my maximum value for N. So now I could just go and start counting these. So if I look at the minimas, followed by the maximas, secondary maximas, then here we go. Just looking at the number, I have to go to the number that's an integer before 12.1, so that tells me immediately that ND is equal to 12. And the number of minimas should then be 2nd, which will be 2 times 12, so it should give me 24 minimas total. So I now know my values now. Now, if I look at my maximas, I got to look at the value of the odd half values. So in other words, if I look at NC, we see that NC should go 1.5, and the number that does not exceed 12.1 would then be 11.5. So this immediately tells me that NC is now 11. And so this is going to be 1 plus 2 times NC. So if I look at that value, that's going to be 2 times 11, 22 plus 1. That gives me 23 maximas. But we're not really done here. The fact that we have 0.1, we have two partial maximas. So when I look at this thing, we do have partial maximas. They'll be dim, but they're still there. And what you're seeing here is that when you look at 12.1, this is really 12 plus 0.1. And these guys right here are the partial minimas. So that tells us then that what we're going to see here is that I'm going to have two partials. So in reality, when we add all of these up, I have 24 minimas, and I'm going to say that I have 23 minimas plus 2 partials. So then summarizing this, we have 24 minimas, 23 maximas, and we have 2 partials. So now, before we plot the intensity, they asked us to look at the phase factor. Now, the phase factor is by far my #1 way to identify where you're at in the diffraction pattern. So the relative intensity is written in terms of the phase factor alpha. And this is written as pi a over lambda times sine of theta. As I just stated here, it is easiest to identify locations on the pattern using alpha. And what we see here is that all minimas occur when sine of alpha is equal to 0. So that means if I look at sine of alpha equal to 0, this tells me here is that alpha must be integers of pi. So this has to be plus pi, plus 2 pi, etc., which is exactly the same value of n. So now if I look at this thing, I could now look at the intensity profile. So if I now draw out the intensity profile, I'm then going to have this. So I'm going to have my central max. Then I got to go out to 12. So that means then I'm going to go 1, 2, 3, and then I'm going to stop here and I'm going to say, and then I'm going to go all the way out to the 12th, and then I have a partial right there. So let's start labeling these guys. And so I know that this right here is 90 degrees. Now, if I was to follow the full pattern, it would look something like this. So here I go. I have the relative intensity. So I know that my n value should be 1, 2, 3. And then this guy right here, this should be 11, and this one should be 12. Now, if I look at my approximate locations for my maximas, they're going to be every odd. And so when I get to here, this will then be 11.5, and this peak here will be 12.5, which is not there. So what I'm seeing here is that this little tiny spot right there, this spot right here, this value right here is 12.1. Now, if I go and I zoom here, if I zoom in, what I'm really seeing is that I'm seeing this here. This thing is going up. And it's looking like this. And this is the point where this is 90 degrees. So if I look at the location of my minimas, right here, this is 12. Right here, this is 13. So once again, you could see here is that this guy is just past the 12th minima. So if I look at my alpha values, which is my preferred way to identify things, I know that these are going to be pi, 2 pi, 3 pi, 11 pi, 12 pi, right? So right here, this is going to be 12 pi. This is going to be 13 pi. And if I look right in here, this is going to be the odd values right here. So then the odd values should then be 1.5 pi. You see, I'm going to run out of space. This is 2.5 pi. And then I'm just going to keep going, and I'll just draw it over here. And then this guy right here is then going to be 12.5 pi. So there's my diffraction profile. So now let's go to B. To calculate the separation, the screen separation between the first and second minima, we must solve two equations. Just as we talked about in lecture. The process is calculate the angular locations from a sine of theta, the path difference equation that is, and then use the screen location equation to get y of n. So let's do that. So the angular and screen locations are then going to be as follows. So when you look at these things, we're only interested in theta 1 and theta 2. In other words, we only want n d equal to 1 and 2, and that's it. So if I look at this thing, I could then see that theta of n from the path difference equation is then going to have sine of inverse of nd over a over lambda. So now if I put these values in, I'm going to have theta 1. No, let's not write it like this. It's going to be sine inverse of 1 divided by 12.1. And when you calculate this, you get plus or minus 4.74 degrees, and that's going to be theta 1. Now, if I do the exact same thing here, then what I'm going to get here is that I'm going to get plus or minus 9.51 degrees, and that will be theta 2. So when I look at this thing here, here is my angular locations. Now, I'm wondering if I could put this on the same line. Let me see if I can do that. So now, if I go and get the screen locations, then I know that this is going to be y of n, and this is going to be d tan of theta n. So then when I calculate these guys, this is going to be 3.20, and this will be tan of 4.74 degrees. And of course, this will be 3.20 tan of 9.51 degrees. And when I compute that, I'm going to get that this is going to be plus or minus And I'm going to write this in centimeters because that'd be easier. Well, maybe I should have. It's going to be 2.65 meters. And this is now y1. And then this will be plus or minus 0.536 meters, which will be y2. So now I have the angular and screen locations of the first two minima. So now what we can do is that the distance between the first and second minima is then going to be delta y, which will then be y2 minus y1, which will then be, this will be 0.536 minus 0.265. And the value that I get here is going to be 27.1 centimeters, not meters. And that's what's going to be my separation between them. Now, there is a nicer way to do this. And the way, so I would say here is that there's a nicer way to do this. By recognizing that minimas minima separations are all equal. So that is that if I now look at my diffraction pattern again. So let's say that this is my diffraction pattern. And what I'm going to do here is that I'm going to draw out the first two secondaries. So when I come out, I'm going to come out here. And when I'm looking at this thing, what you're seeing here, what we just computed was the distance between N1 and N2. So in other words, this guy is 1, this guy is 2, and of course this is minus 1, and this is minus 2. So if the minimas are the same distance, what this is really telling me here is that the distance from here to here and the distance from here to here are all separated by y1. They all have this, they have the same separations. So another way that I could have calculated this, I could have said that delta y is then going to be y2 minus y1, but y2 is just twice the distance from y1. So then you could have seen here that this is now just y1, which is 26.5 centimeters. But if I approximate that, I get 27 centimeters, which matches well with what we just got. And another thing to realize is that you can see here that the central max has to be separated also by 2y1. So I could just start counting, but as I get farther from the central axis, what I'm going to find here is that now I have to worry about my angles here not being accurate. So let's now go to C. So what C wants to calculate is we want to calculate the following thing. We want to calculate the width of the central max, and we want to calculate the screen location of the secondary maxima. Okay, so from our discussion in part B, the width of the central maxima is then going to be delta y central, which will then be 2y1. So if I multiply that number, I get 0.536 meters. I should have written this in centimeters. And this is the width of the central max. Now, following the same game as before here is that now what I want here is that the screen location of the secondary maxima is approximately centered between two minimas. So now if I draw up my picture, I can just count. Instead of actually doing a series of calculations, I can just count. So if I now look at my pattern, it's going to look something like this. So my relative intensity is going to have, I'm going to have my central max, then here's my first, and then here's my second. So now if I start to look at their locations, following what we just said, so the approximate location, right? So I know that this is 1, 2, 3, and then we know that these are approximate values of 1.5, and this is 2.5. Well, you can see here that that's really just 2.5 of the separation of one minima. So in other words, you can also see that the distance, so the location of NC equal to 2, we could then see that this separation for NC equals to 2, maybe I should write it like this instead. Well, first I got to get to the second minima. So this is going to be 2 times y1. And then we're going to say that it's approximately between 2 and 3. So then this is then going to give me 1/2 of one of these. So this will then be 2.5 y1. So if I just plug in my numbers, the value that we end up getting here is 66.3 centimeters, and that's an approximate value for the location of NC equals to 2.